So this problem is a little tricky because we have to make sure we're really careful with our terms. So what we're going to say is that the energy get a spacecraft from the Earth to the Moon will mean sitting at rest on the surface of the Earth and then landing at rest on the surface of the Moon, although both of those are not really true because a spacecraft on the surface of the Earth is not at rest. It's already rotating with whatever its speed is on the Earth. It actually gets kind of weird because it's different from launching from, for instance, the North Pole to the Moon, because then you're not spinning with the Earth if you're at the North Pole, so you don't get the same boost. But we'll assume we launch from the equator, if only because the Moon orbits in the ecliptic plane, the equatorial plane of the Earth, and therefore you're most efficient doing that. So we're sort of saying that we have the following situation. So we're looking now from above the North Pole, so the Earth is rotating, and the Moon is orbiting the Earth. We can neglect the rotation of the Moon because we know that the Moon is tidally locked to the Earth, so it's rotating in such a way as to always keep the same face towards the Earth, so its rotational speed is equal to its orbital speed, so I don't really have to worry about that. In both cases, of course, we're going to have essentially something that looks like this. The energy is going to be potential energy due to the Earth plus potential energy due to the Moon plus the kinetic energy of the situation we're in. So we'll just need to sort of find that for case 1 and case 2. Case 1, case 2. And then whichever one has the lower energy needs to add the difference, and so it would answer that question. So we just need to find the total energies. So I'm going to go do that on the screen. My first step going forward is to recognize that I really want the energy per unit mass, since it just scales with the mass of the spaceship. So I'm really looking for all my energies divided by m, and so they'll cancel out. So I want like the kinetic energy per unit mass and the potential energy per unit mass and so on. And then I think I want to just say, let's find those. So for instance, the kinetic energy per unit mass in case 1 is 1/2 mv squared, case 1, over m. And so the mass of the spaceship has gone away. And then I'm going to recognize that v1 can be written as the radius of the Earth times the rotational rate of the Earth. And that all squared, of course. So I get 1/2 re squared omega 1 squared. And then I remember that omega can be found because it's 2 pi over the period. And the reason for doing all of that is that I know the period. So this is 1/2. The radius of the Earth is 6.4 times 10 to the 6 meters, quantity squared. And here I'll have 2 pi over 1 day, but then I have to convert the day to seconds to get everything in the same units. So 24 hours per day, and 60 minutes per hour, and 60 seconds per minute. And then we can get a number. 108,308 joules per kilogram. All right, which doesn't tell us a lot to begin with, but we can get the potential energies and go from there. Likewise, the potential energy from the Earth divided by the mass ends up being minus gm Earth over the radius of the Earth, which has a value of minus 62218,593 joules. And similarly, the potential energy due to the Moon at this distance is minus g mass of the Moon over, and remember this was the distance minus the radius of the Earth. We end up with minus 12983 joules, giving us a total energy in case 1 which is equal to minus 621,23268 joules. I'm carrying ludicrous precision, but I don't think it'll matter in the end, so we'll find out. Anyway, we can do the same for the second case. So the kinetic energy per unit mass is 1/2 times v2 squared, and then v2 would be the radius of the circle tracked out in that case times the period of the motion in the second case, but the radius is going to be the distance of the Moon minus the radius of the Moon because we're back a little bit towards the Earth, And you get kind of this mess, remembering that the period now is 1 month, and there are 27.3 days in 1 month for an orbital month, and so we end up with a number which is 518,435 joules. The potential energy due to the Earth per unit kilogram is going to be minus g mass of the Earth over the distance between the satellite and the center of the Earth, which in this case is now the distance between the Earth and the Moon minus the radius of the Earth, minus the radius of the Moon, and that number comes out to be minus 104,1696 joules. Likewise, the potential energy due to the Moon would be minus g times the mass of the Moon over the radius of the Moon, which will turn out to be, I guess these are all per kilogram. Turns out to be minus 2817500 joules per kilogram, and so the grand total for the energy in case 2 per unit mass is minus 3340761 joules per kilogram. So putting together these two results, we see that in case 1, when we're sitting on the Earth, we have a much lower energy than the energy on the Moon. We need to add a lot of energy on the Earth to get to the energy on the Moon. So it is much harder to go from the Earth to the Moon than vice versa. Based on the reasons they give us, the only answer that matches our answer is this one. There's less energy required to get to the Earth, go from the Earth to the Moon. Their argument here is probably sound, which is that the escape speed is less. It's easier to escape the Moon to infinity than to escape the Earth to infinity, so it should take less energy to go from Moon to Earth than vice versa. That was long and roundabout to get to the same conclusion, and if you quailed at doing that, I don't blame you.